Well, thanks everybody for joining me, and it's my first time at Stanford, so very exciting. And it's great to be part of this seminar with such a great group of speakers. So I'm going to talk today about what I call photo mysteries, solving photo mysteries, which is, to me, a very interesting challenge. I'll talk a little bit more about it soon, but this idea that we're going to make sense of photos given little or no context. What's being pictured, when was this photo taken, where was it created, all these kinds of questions. And my approach to try to solve these mysteries is going to be what I call expert-led crowdsourcing. And I'll talk more about that as well. It's basically the idea that experts and novice crowds can collaborate and have complementary strengths that can lead to some really nice outcomes for these investigations. So I'll start with an example that I imagine many of you are familiar with. And this was a terrible tragedy a few years ago, the Boston Marathon bombing. And as many of us know, there was an attack. Some bombs went off, some people were killed, and there was a manhunt to try to figure out who was responsible for this. And it took a while to figure out who that was, who the perpetrators were. And so the police and law enforcement released photographs of the event and the moments before to try to enlist the public's help to figure out what might have happened. Was there someone suspicious? Or is there some evidence that there might be something weird going on here? And so a lot of people and a lot of online communities like Reddit and 4chan and some others took up this opportunity to say, oh, well, we could figure this out. We can solve this mystery. We can catch these criminals, these terrorists. And so they tried, and they created a subreddit dedicated to solving this mystery. And maybe you encountered it, or maybe you heard about it, but lots of different members of this community tried to piece together this mystery, looking at different photographic evidence, circling things that look suspicious, trying to draw connections across them, trying to propose different narratives of the different sequences of events that might have led to the attacks. And unfortunately, this community, Reddit, as well as the other ones, were not successful in identifying the correct suspects. However, they did name some other suspects who turned out to be completely innocent. So it was a real disaster, and kind of a tragedy upon a tragedy for those innocent people. And not surprisingly, the rest of the world was pretty upset about this. And the news media in particular, who would traditionally be doing some of these investigations and covering these incidents, was really upset and just went to town on the Reddit community and other communities that were trying to do this, calling it a witch hunt, vigilantes. And the community of Reddit responded as well and said, we're really sorry. We're going to shut down this forum. We're going to delete every bit of evidence related to this discussion. And then all kinds of op-eds came out later with, these witch hunts are awful. These amateurs shouldn't be bothering. Crowdsourced crime fighting is a terrible idea, and this basically shouldn't ever be attempted again. We tried it and we failed. So I appreciate that response, and I recognize this as a prominent example of a real failure. But I personally am not ready to just throw in the towel and say crowdsourcing can contribute to these kinds of investigations. It has nothing useful to offer. Instead, I think there might be a nice opportunity here to link up these crowds who are passionate about these mysteries, who want to solve, who may have valuable skills or information, with experts who can help guide these investigations, make sure that they don't go down an unethical path, or that they stay on track. And that's kind of where this idea of expert-led crowdsourcing comes from. And so, as I mentioned at the beginning of the talk, it's kind of a simple idea. I think that experts and crowds can have complementary strengths. Experts have this domain knowledge. They know a whole heck of a lot about a specific topic. But they also have limitations. They're individuals. They only have so much time and energy they can commit. There's only so many leads they can follow up on. And in contrast, crowds rarely have that domain knowledge, at least the novice crowds that I typically work with. However, they have a lot of energy. There are typically lots of them, So they could potentially work in parallel, they can collaborate, they may have local knowledge or diverse knowledge that the expert might not have. And so there's some exciting potential here, I think, to imagine how these two different groups could work together on something like a photo investigation. So the work that I'm going to talk about today is trying to imagine how that could look in the context of investigations like the one that I mentioned earlier. And it kind of draws on a lot of previous work in crowdsourcing primarily. A lot of it was performed here at Stanford, and some of those folks may even be in the room. But there's been a lot of really important previous work that I'm building on here. So there's been studies of how leaders can lead a crowd, and maybe a novice or maybe an expert can have some kind of direction or delegation performed with that crowd. Crowds that are composed of experts, like the Flash Teams work explored here. We have lots of different people with different expertises, how we can combine them to get some kind of great result. Crowd sensemaking. Sensemaking, the idea that we're trying to understand a situation and we don't really even know where to start. We have to develop our own schema of what's even happening before we can start to piece it together. Crowd visual analysis, everything from projects like Jeff Bigham's VizWiz project, where we're helping blind people recognize objects in their environment using crowdsourcing, all the way up to some of the crowdsourced visual design critique work that I've done, and using crowds to analyze things like Google Street View images looking for evidence of accessibility issues. And finally, if these crowds are going to be interacting with experts, it probably needs to happen in some reasonable time frame. So there's a lot of really nice work here from the Adrenaline project early on through Walter Lasecki's work with Chorus and Legion, some real-time crowdsourcing, to most recently work here exploring how we could very quickly categorize images using crowds. So I'm trying to build on the shoulders of giants here, excluding myself. and hopefully the result will be something really even more exciting than what we currently have. So this domain of crowd investigations in the context of something like the Boston Marathon bombing can be narrowed down a little more specifically to a task called image geolocation. So here I'm talking about, given a photograph, where exactly on a map was this photo taken? I'd like to pinpoint that as specifically as possible. And this is one of several, or really endless questions you could ask about a photo. You could say, who was in the image? When was it taken? For now, I'm focusing on where. Where was that image taken? And more specifically, I'm talking about a wide variety of images that might be geolocated, images that might come from eyewitnesses to a crime or government posting images of important events that are taking place, or even terrorist or criminal organizations posting propaganda. A lot of this is coming in through social media, photos and videos. And I'm going to talk about this more, but experts in this field, they're typically performing these geolocation tasks manually. They are often using open source tools, a wide variety, I'll talk about that as well. And it's often a manual process, synthesizing this information, making sense of it, whittling down the possibilities. So here's some examples of the kinds of geolocation tasks we might be interested in. And you can get an idea of the variety. And there's a lot of really interesting examples of this work being performed online, some by experts, some by online communities of citizen investigators. One of them is known as Bellingcat. You might be familiar with that. A lot of really interesting examples on that site. And what you can see in this example, here is a photo. This is actually from a video of some Tunisian jihadists. And it was posted online, and folks were trying to figure out where it was taken. And they were able to use some clues in the images, some distinctive architecture, to then identify a probable region. This turned out to be Raqqa, and use this aerial satellite imagery to narrow down the exact location where that distinctive architecture was present and ultimately identify where they were. And another example, these are some pro-Russian trainees that were posting photographs of their training camp on social media and trying to keep the location a secret. But the online communities were able, this particular one is Bellingcat again, were able to identify this location from some of the distinctive geographic features and ultimately figure out this camp's location, which was just on the edge of the Ukraine-Russia border, I believe. And this is valuable information that can then be used to corroborate or dispute what claims are being made either by a government or by the source of these images. So give you a little preview for what else I'm going to talk about. Basically, what I'm going to start with is I'm going to try to dig deep into understanding how these experts perform these geolocation tasks. And I gave you a couple of examples, but overall, we don't really know how they do it. We don't know what their process looks like. We don't know what their challenges are. We don't know how someone might be able to help them, how a crowd might be able to help them. So following that, I'm going to show a system that we built called GroundTruth that is informed by these studies with experts and ideally will help them perform their geolocation work using crowdsourcing. Then I'm going to talk about a couple of experiments that we ran with crowdsourcing platforms to explore how a novice crowd might be able to do something as difficult as an image geolocation. And then finally, it's not really 4 studies, it's really 3 studies and a little teaser of a 4th study. I'm going to give you a couple of examples of how experts are using GroundTruth software for geolocation work. So let's jump in. So starting out with this first study, I'm really trying to understand what does geolocation look like from an expert's point of view. And as I mentioned before, this is a manual process for the most part. They're using a lot of different kinds of tools. They're synthesizing a lot of different kinds of information. How? What exactly is going on there? So we conducted interviews with a bunch of expert geolocators in different domains, each one about an hour long. We were asking them about their motivations. Why do they do this? What does that process look like? What challenges do they face? Who do they collaborate with other experts or with the crowd or with the public? And what kinds of tools and technologies do they use? And then we did a bottom-up analysis of those transcripts. So to give you a sense of who these people were and maybe a sense of what geolocation looks like more broadly, you can kind of see a little bit who these people are and the organizations that they represent. So we have a private investigator, we have a researcher from the Digital Forensic Research Lab. We've got a couple of journalists who work for a company that does social media verification for a lot of major news media clients. We have people who work at large news agencies, and a handful of folks who wanted to remain anonymous. Some, again, working for large news media agencies, and others doing work in security and in intelligence and other fields like that. So it's kind of interesting. You can already get a sense for this process of geolocation is pretty broad. A lot of different domains, a lot of different fields are trying to do this for different reasons. You know, someone at Amnesty International might have a different goal than a private investigator, but the geolocation work, as I'll show, tends to look similar in a lot of ways. So I won't have time to get into all the details of the interview study. I'll just touch on some of the key points that helped inform our software development. But these are the general categories that I'll run through. So just real quick, talking about motivation, I think this is kind of interesting because it helps underscore that although this is a manual process that can be tedious at times, it is also very rewarding to these experts. And they're not necessarily looking for someone to replace them, to do the work for them. They are interested in help, as we'll see, but some of them are really excited about this work. They feel like they're a detective. There's an adrenaline rush. They think there's a moral argument to just debunking these facts, these claims that might be made, especially when when we're talking about people being killed, civilians being killed. And someone who's been a journalist in a few different agencies, there's something appealing about being so close to the raw facts, that they are almost being there, as this one person described. So talking about the process, this is actually a fairly long process. The ones in bold are the ones I'll go into a little more detail on, but very briefly, this is roughly the sequence of steps that a person would go through to perform geolocation. First, they're going to find an image or video that they're going to geolocate, and that may be provided to them, or they may go looking for it. There's a number of ways. Then they're going to try to gather context about that image. Who uploaded it? Where was it found? Was it on Twitter? Was it on Facebook? Is there any metadata associated with it? Are there any comments that have been posted on it? What kind of clues are immediately visible in that image? Are there street signs? Are there geographic features that we can use to draw some conclusions? If there aren't enough clues to immediately identify the location, then the expert will typically draw a diagram, an aerial diagram, that will try to convert that ground level photo into an overhead view. And the reason they're doing that is because they're then going to take that overhead view, that diagram, and try to compare that with satellite imagery in Google Maps or in TerraServer or one of these other satellite image sources, and try to compare visually the two different, the drawing with the location in the real world. Then they'll do the search itself, going through systematically, trying to figure out, okay, this isn't it, this might be it, looking in the entire search space, however broad that might be. At some point, they might find what they're looking for, or they might not. And then at that point, they have to know when to quit. Okay, this isn't going to work. I'm not going to find it, or too much time has passed, it's no longer important. And then finally, they'll report that result. Depending on who it is, they might be writing up a report for a client, or they might be writing a news story for the public, or some other kind of dissemination. So digging a little deeper into some of these steps. Gathering context. This is kind of differentiating between identification tasks and verification tasks. If this image or video is just totally on its own, then we don't really have a whole lot of context. But there might be some claim associated with it. The government is saying this photo was taken here, or it was taken on this date. And we're going to gather as much of that information as possible. If there's metadata, we're going to maybe use software to grab any geotags or any EXIF data, what kind of camera was used. But most social media platforms will scrub this data, so it's not available. The process of looking for clues, this is kind of amazing, all the different kinds of clues that the experts talked about using. Really, the list is endless. They were looking at signs, they were looking at logos. More surprising things, the shadows can be used to determine the time of day, different weather patterns, vegetation, you name it, they looked for it. And then there's the image itself, not what the content of the image is, but how grainy is it? If it's grainy, it may have been republished, and we may question that source. Has there been any obvious manipulation, or advanced tools like tungsten can be used to detect any manipulations? And ultimately, they're looking for these clues because they're going to try to synthesize them and narrow down the possibilities. For example, if they have narrowed it down to a city and they see a gas pump, then maybe they can go and research where are all the gas pumps in the city, and then they can systematically go through each one. So they're synthesizing this information together to reach a conclusion. Some other techniques that they use, again, they're pretty much endless, but a couple that impressed me. One group was looking at recent satellite imagery and noticing these craters. The craters were actually from mortars that were fired, and the shells hit the ground in a particular pattern. And it turns out you can analyze that crater to determine the location of the mortar that fired it, depending on the width of the radius and all those kinds of things. So this is the kind of work that can be done. And this other example, claim was made about a certain kind of missile truck that was in the area, and the researcher knew the turning radius of that particular vehicle and was able to look at these tire tracks in the satellite imagery and determine, well, that particular truck couldn't have made those turns, therefore it has to be something else. So incredible creativity, incredible variety. And as I mentioned, sometimes those clues aren't enough, and so these experts have to draw a diagram. So what they might start out with is a video, or in this case, a video. This was a sad incident where a reporter was killed in Cairo. And from this video, they might have to patch together different scenes. They'll produce an aerial overhead diagram that reflects the structures, the key distinctive elements and structures in that video. And then they'll comb through satellite imagery of that location and try to find a match. And it can take a long time, or it may never work out, but as you can see in this case, they were able to figure out where exactly that attack took place. And once you have developed this diagram, you have to compare it against something. So you need to go and find some reference imagery. And different services are better for different locations. For example, Google Street View is great for the US and select other countries, but a lot of countries don't have Street View. And in some cases, Bing has better satellite image quality than Google Maps does, or Google Earth. The experts had very specific claims about which of these services were better in different situations. They also use a lot of non-satellite imagery to kind of get a feel for the area. They'd look on Flickr, they'd look on Panoramio, which unfortunately no longer exists, and try to see other kind of on-the-ground evidence. So as I mentioned, there are other steps involved, but I wanted to give you a feel for the most critical steps in the process in terms of this work. We also asked those experts about crowdsourcing and whether or not they ever used the public, asking for tips or seeking specific kinds of information. And they had pretty strong opinions about what crowds should and shouldn't do in terms of helping them with their geolocation work. So things the crowd could do or had done for them, simple, definable tasks. Maybe providing more reference imagery that they might have access to, noticing things that the expert might miss, kind of another pair of eyes. Maybe they might have some specialized local knowledge. They live there, they've been in the area before. They could tell you things that that person wouldn't know who hasn't been there. And then there were other things the crowds they felt shouldn't do that really experts are better suited for. Any kind of analysis work, well, synthesizing, making interpretations of the evidence, anything that required interaction. So it's one thing to gather information that's available online. It's another to go out and ask a source, where did you get this photo? Or go onto the ground out in the field and start talking to people. Any kind of confirmation, the expert is really the person to make the final call about whether this is accurate or not. And then certain topics that were very sensitive, that could really impact people's lives, or the content itself could be very upsetting, maybe best left to the experts. So then, finally, we asked them about some challenges and that they were facing and ways that perhaps we might be able to help. And they had a number of these as well. One of them is certainly the fact that speed is critical to this work. Oftentimes, they need this information within a half an hour or less. And it's interesting to get this insight from one of the experts. He says, I'm a journalist first. I'm not a forensic scientist. So I'm interested in getting the story right, but I'm particularly interested in getting it right for my agency and not having someone else get there first. There's also an issue with using all these different tools. A lot of appliance-like tools that are scattered all over the web. This one participant had a colorful way of talking about it. Go find something like Jeffrey's EXIF viewer, and it's dodgy as a box of frogs. These tools aren't consistent. They may not be reliable. They may disappear. That makes their work a lot more difficult. Very rural or urban areas, not enough clues or just an abundance of clues, overwhelming. Sites like Twitter that will remove metadata, and the subsequent laundering of content where an image is reposted many times and you lose the trail of where it originated. And trolling. The experts mentioned they see an increase in deliberate trolling where people are purposefully trying to mislead them with the content they put up. So some high-level takeaways. We saw these processes and patterns tended to be consistent across these different domains, which is promising for anyone that might want to build any technologies to support these challenges because they might have broader applicability. Experts are already using crowds and crowdsourcing, often in low-tech ways, but they're open to this idea for the most part, and they've had some success. A lot of the tasks that are being performed by these experts, we could imagine some of those things being offloaded to novice crowds, certainly not everything, but they had a variety of ideas for what could be possible. And the experts almost unanimously said they're overburdened. They have too much work to do. There's too many images coming in. They don't have time for all this. So if they could get useful help, they would really embrace that. They would appreciate that. So that's kind of where we decided we would try to jump in and create some kind of tool that would support this geolocation work. And our idea was we would start with this satellite image analysis problem, where we have a bunch of imagery that needs to be looked through, and we have an expert who is looking for a specific thing. And you can imagine a bunch of different ways that might work. And so maybe an obvious approach or a naive approach might be, okay, well, we have a photo and we want to geolocate it. So maybe we have a bunch of satellite imagery and we'll ask the crowds to look at that photo and look for a section of the satellite imagery, and great, maybe they'll find it or maybe not. But we have a lot of reasons to think that probably wouldn't work. Experts talked about how the mental process of translating this image into this photo into an aerial diagram is difficult. It takes practice. It's a cognitive skill that not everyone has. And so what we imagine is that perhaps there's an opportunity to leverage an existing practice of those experts to kind of bridge the gap and allow these crowds to help the experts. And that bridge could be one of these diagrams. Experts are already creating them as part of their own process. What if we could share that diagram with crowds? Would that actually help them do this task easier? Or would it be an impediment compared to something like the original photo? And that's what we aim to find out. So we developed this system that I mentioned called GroundTruth. It's a web-based system. The idea is that the expert produces one of these diagrams like they typically would for themselves, but then they can specify an area of the map that they want a crowd to help them search. And so the crowd will be looking through this satellite imagery at the same time that the expert is doing their own investigation. But the crowd's results can help the expert prioritize, picking the areas that are the most promising, that have the most potential, that look most like the original image. So what I'm going to do is I'm actually going to show a quick video of the system first that we ended up with. And then I'm going to get into some of the details of the studies that we conducted to get it where it is now and explain some of the choices, the design choices that we made. Okay, so this is the expert view of GroundTruth. On the left, you have the source image. This is the mystery image we're trying to figure out. And then here we have the diagram that the expert has drawn, the aerial diagram. And on the right here is the search area. So what they're doing right now is they're choosing a subregion size. I think every time I click it, it makes that noise, sorry. I'll point. So they're picking a size that they want to be basically a rectangle that a crowd worker would look through and compare against the diagram that you see here. So that's going to be based on basically the same size as the diagram that's been generated. Now the expert can turn these, the satellite imagery on and off, they can turn the map and the labels on and off, but ultimately they pick some location they think is promising, and they draw a rectangle like this. So the rectangle will then be converted into a grid, and that grid is now being sent out to a bunch of crowd workers. So here's a crowd worker interface. The worker's been assigned this 16 grid square here, a rectangle, and they're going to go through each one. And if they see something that looks like the expert diagram, they're going to mark that as a yes or a maybe. If they don't see a match, they're going to click no. And this is going to be a kind of systematic process. They're going to go through one of these subregions at a time and ultimately make a final decision. Now, they're somewhat constrained by the interface. So they're really supposed to be focusing on the subregion or the box that they're in at that moment. And you can see the border there kind of helping them. Now, they're allowed to zoom in, and they can pan a little bit to kind of check the edge to make sure that the target area doesn't fall into a crack, so to speak. But ultimately, they're kind of constrained to look into that one area. So back to the expert view, theoretically, they're investigating this on their own pace. And meanwhile, crowd feedback is starting to come in. And these red boxes are the no areas marked by the crowd. And the green areas are the yes, maybe areas marked by the crowd. And the darker the green, the more agreement there was from multiple workers, indicating that this is a more promising area. So what we can imagine is the expert would look at this grid, and if they trusted the crowd, they would ignore the red areas or spend little time on those. And they would prioritize focusing on the green areas. So the expert is turning off this color temporarily. They can mark areas they've already checked in black if they don't find what they're looking for. That keeps them from accidentally searching the same area twice. It's usually easier to investigate if you can turn those colors off temporarily, so that ability is there. And you have access to the variety of Google features. So for example, the 2.5D mode might allow you to make a comparison that's closer to the ground photo. So right around here, I think the expert is going to find something that looks promising. You can see the blue border represents the cell that they're kind of in at that moment. So if they click exclude, then that one turns black. Or if they click found it, that's the area that will be returned as the location that's been found. And sure enough, this is a close match. And they found it. A little anticlimactic, but they found it. Hooray. Okay, so in developing this system, we had to make a number of different choices, and we had to conduct some experiments to really figure out which of these design decisions led to the best results. So these two next experiments that I'll talk about, they're both kind of connected to this question of the diagram. And it had a chicken and egg problem here, because first we were wondering, okay, which would be better for the crowd? Would it be the ground level photo, or would it be the aerial diagram? But the other question we were wondering was, how much detail should be in that diagram? Should there be a little bit of detail or a lot of detail? And we didn't want to compare the wrong level of detail against the ground photo. So we decided we would first start by looking at the level of detail in the diagram. And once we found the best level of detail, then we would compare that to the ground level photo and see which worked best. So that leads us into this next study. We're trying to figure out what's the best diagram that we can provide to the crowd that will allow them to perform this task as effectively as possible. And you can imagine too much detail and they're overwhelmed, not enough detail and everything looks like it and there's too many false positives. So instead of reinventing the wheel, we took some inspiration from other kinds of people who have attempted to abstract or stylize geographic data. So we took a couple of level of detail schemas from the 3D graphics community. And basically, as you go from low to high detail, you start adding more structural detail, you start adding vegetation, etc. So long story short, we ended up with these 6 levels. And they're cumulative, so as you go from top to bottom, you start adding more and more features, and ultimately, you end up with the highest level detail. So for our experiment, we wanted to compare these 3. Okay, so on the one hand, the lowest level of detail, just the bare minimum road boundaries. On the other extreme, high level, we're talking about trees, bushes, that kinds of stuff. And then a middle level. And that's what we're going to be experimenting with and exploring. Now, there's some questions here, of course. What are the right images to even use to draw these diagrams? Well, we were lucky to find a training set that one of our experts used for doing geolocation workshops. So we figured, okay, if these are considered good for training novices, those seem appropriate for our purposes too. The next question is, how much work should we give any individual worker? And you know from the video that we're asking workers to look at 16 different subregions per worker. It might seem like a lot for a crowd worker. Why not just make it a micro task and have one region at a time? And we tried that, and we found that we weren't getting good performance. There wasn't enough context. And very often, the subregion would be too small, and they wouldn't get the full picture. Some of it would be cut off, and they would mark that as a no. And then it would come around to the other half later, and they would mark that as a no as well. So we explored different amounts. We tried grids of 25, and ultimately grids of 16 turned out to be the right amount for optimal performance. And finally, how do you navigate these 16? Should they just go randomly? Should they go in a straight line? Once again, we can draw on some smart people from other domains to help us here. So search and rescue communities think about this all the time. Depends on kind of what you're doing. If you have a good idea of where your starting point is, you might use the expanding square pattern, or if you're using an airplane, you might use this sector search. But we're going to use the creeping box because that's been found to be the best strategy when you don't really have any idea within the region where the location is likely to be. So these are the diagrams that we ended up producing. And you can see we have low, medium, and high detail diagrams for 3 locations: Brasilia, Los Angeles, Charlotte. And these are, you can see as we add in more detail, we start to getting vegetation, road markings, things like that. These are going to be those 3 levels that we're exploring. So we conducted an experiment on Mechanical Turk. And we have these 3 levels of detail, and we have these 3 locations. Each worker is getting this grid of 16 regions, subregions. One of them is correct, 15 of them are wrong. And 60 workers are going to be assigned to each combination of a level of detail and a location. We gave them all 10 minutes because we wanted this to be a pretty quick process. If everyone takes 10 minutes, then theoretically, we could have all the results back in 10 minutes because we can parallelize. And we paid them minimum wage for our location based on the amount of time that we saw most people take. And we measured 2 things: the quality of their results, how accurate they were basically, and prioritization, how successfully would we be able to recommend the most promising subregions to that expert. And one final point to make here is that this is a certain kind of problem. There's a lot of different, especially commercial satellite image analysis sites where people are looking for certain kinds of content. They're marking damaged buildings, or they're looking for certain kinds of structures. This is a needle in the haystack problem, which means that we are looking for only one thing, because it's a geolocation. There's only one location like it, and it's high importance. If we miss it, we're in really big trouble. So has anybody found the one that's not a Q yet? All right. Well done. That's the best I've seen so far. It is indeed over. Here we go. Ta-da! Right. So that's what we're trying to do. So the obstacle we're facing here is a cognitive bias from called the prevalence effect, which, big surprise, says that if there's only one thing, people get tired after a while and they stop looking for it and so on. And this is really important for us to overcome because this is fundamentally what we're trying to do for geolocation. So we're going to look for two things to try to get around to try to measure this properly. First, we're going to look at the true positive rate, which means that if a subregion was the correct one, how often did people say that was a yes? And then for the opposite, false positives, we're going to say when this subregion is a no, and when it's not the correct one, how often do people say that it was a yes? Those are the two measures we're going to look at. Finally, when we were running this study, we first did some pilots, and we found that these individual workers, if we asked one person to look at each subregion, we didn't get very good results. Some people just weren't very good at it. They didn't try very hard. We're not sure, but they didn't do so well. So we wanted to try different kinds of aggregation, have multiple workers do the same task and aggregate or combine their results in different ways. We tried a bunch of different things. Ultimately, what we found was a one yes rule for a group of 3 workers yielded the best results. So for every region, we're going to have 3 different people look at it, and if any one of those people says yes, we're going to mark it as a potential yes. And when we tried 2, the results weren't so good. When we tried different larger groups of workers, 3, 5, 10, results weren't so good. This turned out to be the best balance of the 2. So that means that we took these 60 workers that were in a condition and we randomly formed groups of 3 for our analysis. So we ended up with 20 groups of 3 workers. All right, so what did we find? So first, looking at quality. This is interesting. All of the workers, regardless of the level of detail, did pretty good at finding the correct region. So in the low and high detail case, about 92% of the time, they marked the correct region. In the medium detail case, they found it 98% of the time. So they're not missing it very often. What we didn't find is any difference between the levels of detail. Now, sure, in this particular experiment, medium did a little bit better, but it wasn't a statistically significant difference. Of course, finding the right region is only important if they're marking a lot of other regions as not correct. Otherwise, you could just mark the whole thing. So we have to look at the false positives as well. And here we're seeing that regardless of which of these 3 levels of detail, we're getting about half false positives. So that means that we're cutting down the search space by about 50%. And we're still maintaining that correct region 92 to 98% of the time. So looks promising. Once again, we're not seeing a difference in the level of detail, although medium seems to be doing a little bit better in both of these in this particular case. So moving on to prioritization. All right, so can these experts get suggested the more promising locations better than chance? So when I say prioritization, I'm talking about of the group that we have marked as a yes or a maybe, how often do more than one worker agree that that location is correct? So we're using that agreement to come up with a prioritization scheme. Now, because there's only 3 levels of agreement, 1 worker, 2 workers, or 3 workers, we'd expect 1/3 to be kind of our chance. And happily, we see better results than that. Anywhere from about 70 to 85%, we're getting that better prioritization. That means we're correctly sending that expert to the locations that are promising, that contain the correct subregion. So what we see here is regardless of the level of detail, we see the false positives cut in half while maintaining almost perfect true positives. We did see slightly better results for medium, but not significantly different. For the prioritization, all of them were significantly better than chance, and the low detail seemed to be a little bit worse than the others. So what we can conclude, I think, here is that the diagram does show promise. Remember, none of these people saw the ground level photo. So the diagram shows promise. Medium seems as good as anything, maybe a little bit better. So we'll move forward with medium. We have to pick one of them. So then our next question becomes, is this medium level diagram actually going to be any better than just showing someone the photo? Does this abstraction actually improve accuracy or improve efficiency? And that's what this next question is. So we're going to compare some crowd workers seeing the ground level photo, other ones seeing the diagram, and other ones get both and they get to flip back and forth. So maybe the shotgun approach is best. We'll give them both and they can choose when they want to look at one or the other. So what we did was we took those diagrams, and here are the corresponding ground level photos. Again, this is from the training data set. And since we're directly comparing diagrams to photos this time, we did some redaction of the diagrams to show camera position. Because this content isn't visible in the ground level photos, it wouldn't be a fair comparison. So this is what we're looking at now. The study is pretty much exactly the same setup, except that in this case, the manipulation is diagram, photo, or both, instead of level of detail. And everything else was the same. So we can jump right into the results. So looking at quality, we find that using just the diagram is significantly better for true positives than just the ground level photo. So if we provide someone with the ground level photo, they're going to get it the correct location 78% of the time. Maybe not good enough. If this is a needle in the haystacks problem and we know that that crowd worker is going to miss this 1 out of 5 times, we may not want to use crowd workers if we're giving them the ground level photo. But if we're giving them the diagram and we get this 98% true positives, now we're talking. Now this is a situation where the diagram is clearly better and it's good enough that we might actually want to use it. The both turned out to be almost as good as the diagram, but not quite as good. So surprisingly, perhaps, it's better not to show the photo than to show just the diagram. For false positives, very similar across, no significant differences. Once again, we're getting that 50% error rate. So we can say a couple things about this. We can say, all right, regardless of which reference material, we're going to get about 50% return rate, which is pretty good. And more than that, the increase in true positives that we get with the diagram doesn't result in an increase in false positives. So there's no cost to using the diagram. So last thing is, let's look at that prioritization again. Prioritization, again, telling us if we're pointing that expert to the right locations using agreement. No significant difference. These are all basically similar. The ground level did a little bit better in our experiments, but it's not a significant difference. And once again, these prioritization levels are pretty good, about double what we would get from chance. So a couple of conclusions we can draw from study number 3. As I suggested a minute ago, we're getting much better true positives with the diagram and a realistic level of quality that we could actually imagine crowdsourcing this. Regardless of which technique, we're getting about 40 to 60% false positives, so we're cutting down that search space by about half. And again, that prioritization holds up. We're getting about double the prioritizations that we would get from chance. So we're really focusing that expert on the most important areas. So finally, and again, this is just a little bit of a teaser. This isn't a full study yet. We want to actually bring experts into the loop here. And conveniently, we have some experts from our interview study. They told us all the things that were hard about this and all the things they would like to see. And so we went back to them and we said, hey, we listened to you and we built this big piece of software. Would you actually like to try it out on some tasks? And we're kind of in the middle of doing that right now. We've had a handful of people try it already. I'll give you a couple of their high-level comments so far. But really, we want to see how this helps them. And our idea right now is we're going to give them 3 tasks and 30 minutes to do them, to kind of simulate that hectic real-world environment where they have a lot of work to do at the same time. And the parallelization of the crowd could be a real advantage here. So some examples of what the crowd and expert produced. So here's the test image we provided. Here's an expert diagram. And here's some crowd results. Again, we're seeing that 50% area again. Here's another one. These diagrams are pretty interesting, at least to me. And then finally, one more example of the Los Angeles location and the crowd results. We did some interviews after these tasks. We asked people to talk about if they would really use this or what their reactions were. This particular participant, one of the journalists, really emphasized the multitasking advantages of this. So he says, I'm going through this video and I'm doing all these different things, blah, blah, blah. If I was doing that and I could say these are the coordinates for the town and use this search radius and these are the things I'm looking for, I could probably do it in 60% of the time that it would normally take. Well, that's an empirical question. We'll find out, but I hope he's right, and I think he might be. Some other comments, people talking about what it was like to get that crowd feedback and how they integrated it into their work practice. Experts were saying, oh, so yeah, I'm taking advantage of that feedback. I'm looking where the darkest greens are and I'm zooming in there. I paid more attention to those and less attention to the red. And this particular expert who performed the best and got all 3 locations actually completely ignored the red locations, said, forget it, I'm just going to go with the crowd's word on this one and focus on the greens. So for next steps, we're excited to complete that study, get more experts running through using the system, and understand how it affects them, their performance, their attitudes, how it changes their work practice. We also want to do a longitudinal study where they're using real images. They're performing real geolocation tasks on images that they need to identify for their jobs. We're also interested, kind of beyond this whole satellite image ground truth problem, what other elements of the geolocation process might crowds be able to help with? We're mostly focusing here on this process of mapping a ground level photo onto satellite imagery. But that process was quite long, and as you saw, there are a number of different steps like gathering context or looking for clues in the image content, where we could imagine crowdsourcing with its variety and its parallelization could be an advantage as well. So for some final thoughts, just kind of wrapping this up, as I said at the beginning, I think that experts in crowds have some complementary strengths, and that empirical studies like the one that we performed can help us show us what the experts need and where the crowd might be able to help. In this case, we're looking at geolocation, and we saw that with this ground truth system, crowds that use the diagrams can narrow down that search space by about half while maintaining the correct location and prioritizing it about half as well as chance. And then finally, geolocation is kind of one domain or one example of where expert-led crowdsourcing might be valuable, but I think there are likely to be many others. And so I encourage all of you to consider or contribute to thinking about what those possibilities might be. How could we get these complementary strengths working together? I think there's a lot of potential there. So that I will say thank you, first of all, to my wonderful students that worked on this project, a combination of computer science and national security students. We also had a number of participants from Mechanical Turk, as well as our experts and many others. And of course, my funding, and I want to thank all of you for listening and being a great attentive audience. So thank you. Yeah.
So I'm sure there's no machine vision in this at all. There are certain contexts in which it seemed like machine vision techniques could be helpful. Like for example, that one where you had like the rooftop features and like the Middle Eastern men and stuff. Like, have you considered like hybrid approaches, or like did they just not help? Or
great question. Yeah, I'm really excited about the potential for hybrid approaches, and there's actually been some pretty nice work in the computer vision community on geolocation. Different approaches, scene classification, there's some neural net stuff more recently. I think there's a mixed initiative system that has a little bit of computer vision and a little bit of crowdsourcing might be the best of both worlds. We haven't really explored that too much yet. What we saw is some of the main limitations of the computer vision approaches is they often require either a really big database or a really specific idea of what you're looking for ahead of time. And in this case, we didn't really have either of those things. So the crowdsourcing approach may be a little bit more general purpose, but I'm excited to talk to other experts in computer vision and see if there's an opportunity there. Yeah.
Yeah, I just want to continue or kind of comment on that question. It's actually it seems like recognizing contours that you boiled it down, or the experts have boiled it down to a really shallow computer vision problem, and you know, you have these people in Virginia basically doing pattern recognition on a street view from LA. And they're doing what their people aren't really good at, which, like you said, you know, looking for the O in the pile of keys. Mm-hmm. And without any comparison at all to even a weak computer vision attempt at a solution, it's hard to take this seriously.
Well, that's a fair comment. I think one thing to keep in mind is that this practice is pretty much a manual process right now. What we know from our expert interviews is that the experts are doing a lot of this work on their own. So they're using open source tools. They might be doing some collaboration with fellow experts, but most of this is just them sitting at a computer processing this information. So it seems like there's a fruitful area of work for considering ways to help these experts. Our approach is to take crowdsourcing and bring it into this equation. But I could imagine computer vision approach is working well also. Another important thing to keep in mind is these reference images that are being used, the satellite images, come from a variety of sources. Some of them are from Google Earth. Some of them are from very recent images from TerraServer, stuff that was produced maybe in the last day or two. So if we have automated techniques, they need to have access to all of those data sources. We need to make sure that all the latest satellite tiles from the last day can be fed into our reference database. We need to make sure that images from Bing and other services can be used. So if we don't have that infrastructure, it may be more difficult to easily move between those sources. What's nice about the crowdsourcing approach is it's a little more generic. We can point a crowd or human to any of these sources with very little overhead and say, here's an image source, go for it. So there's kind of a setup cost there that's reduced. Yeah?
What I like most about this was the magical step for me is when you use an expert to take the front-on vision of the building and have the expert think about what it would look like from the top down and have a nice, simple representation of that then was interpretable to me. In fact, the streets were more interpretable than the first one, when it had like boxes and lines. That seems like an extraordinarily hard machine vision algorithm to know how to map that, because those things aren't accurate. They're very much cartoonified in a way that humans really know how to do that well. So those abstractions seem to be the key thing that the experts could add to the system to help guide novice users. That diagram.
Right. Yeah, exactly.
I'm wondering if there are any other representations that experts have that you thought could also use this sort of approach at, like representing it right way, then lets people make it a matching problem.
Yeah, that's a great point. I'm just kind of reiterating what you said, but it's an abstraction, but it's not a perfect abstraction, right? And luckily, this kind of diagram is interpretable by a human, and so they're able to say, well, even though the proportions aren't quite right, the gist of it here seems to be well within the range that we're looking for. Maybe to some extent, some of those same fuzzy matches could be accomplished with computer vision. Ultimately, though, we still have that expert at the end of the day that's able to say, well, this was flagged as a potential match, but I have the ability to make that final call. Yeah, it's good to think about what other possibilities might be recognizable by a human that's a little more abstract, a little more stylized.
I think that's all we have time for, but please come talk to Kurt after, so
Oh,
thank
okay.
you.
Thank you.